Welcome to a visual exploration of inner product spaces, one of the most beautiful structures in linear algebra. An inner product space is a vector space equipped with an additional structure, a way to measure angles and lengths. This structure allows us to compute lengths of vectors, angles, and determine orthogonality. Let's look at the formal definition. An inner product is a function that takes two vectors and returns a scalar, satisfying four key axioms. Axiom 1. Symmetry. Axiom 2. Linearity in the first argument. Axiom 3. Positive definiteness. Axiom 4. Conjugate symmetry. We often use angled brackets to denote inner products. This is cleaner and more general than the dot notation. Angled brackets emphasize that different vector spaces may have different inner products, not just the Euclidean dot product. The Cauchy Schwarz inequality is one of the most important inequalities in mathematics. It tells us something fundamental about inner products. The absolute value of the inner product between any two vectors is at most the product of their lengths. Let's understand this geometrically. The inner product can be expressed using the angle between vectors. Let's build intuition for why this inequality is true. We'll use a visual proof approach. Here's vector v. When we project it onto vector u, the projection length is v times cosine theta, which is always less than or equal to v's length. Multiplying both sides by the length of u gives us the Cauchy Schwarz inequality. Let us work through three numerical examples to see the inequality in action. Example 1. Orthogonal vectors. When vectors are perpendicular, the inner product is 0, which is clearly less than the product of lengths. Example 2. Parallel vectors. When vectors point in the same direction, we get equality. This is the maximum possible value. Example 3. General vectors at an arbitrary angle. Let us verify the inequality with 3D vectors. Now let's explore the Gram-Schmidt process, a powerful algorithm for creating orthogonal vectors. The key idea: repeatedly subtract projections to make vectors orthogonal. Let us visualize Gram-Schmidt in 2D step by step. We start with two non-orthogonal vectors. Step 1. u1 equals v1. We keep the first vector unchanged. Step 2. Project v2 onto u1. This gives us the component of v2 that points in the direction of u1. Step 3. Subtract the projection from v2 to get u2. Now u2 is orthogonal to u1. Now, let's expand our view to 3 dimensions. The process is exactly the same, just with one more step. Step 1. Keep the first vector version 1. This becomes our u1. Step 2. Remove the shadow of v2 on u1. Now u2 points straight up the y-axis. Step 3. Remove the shadows of v3 onto both u1 and u2. The result: u3 points straight up the z-axis. We started with skewed vectors, and now we have a perfect, mutually orthogonal basis. Let us see the complete algorithm with a numerical example in 2D. 1. u1 equals v1. Simple. 2. Compute the projection. First, calculate the inner products. Now compute the projection vector, 5/10 times u1. 3. Subtract to get u2. 1 minus 1.5 is negative 0.5, and 2 minus 0.5 is 1.5. Finally, verify orthogonality. The inner product of u1 and u2 is 0. Perfect. Let's recap everything we've learned about these two fundamental theorems. These theorems are deeply connected. Cauchy Schwarz ensures Gram-Schmidt projections are well defined. Beautiful mathematics. Thank you for joining this visual journey through linear algebra. Keep exploring.